Hello, college statistics students. This video is for chapter 10.1 to 10.4, actually 10.1 and 10.4, comparing population means of from two samples. We were running on talking about the steps on how to do the hypothesis test using StatDis, and we stop at writing the conclusions based on what you did for the p-value. If p-value is low, that means you have a real sample comparing to x0. X0 is what? Is always that the two mean are the same. They don't have no difference. Mu1 is equal to mu2, or the mean difference is 0. So when you subtract the pair difference, it's come up to be 0. So there are no difference. And the alternative hypothesis, in this book they use HA. Yeah, they use HA. So this should be A, right? I'll change it in the notes. So that would be either greater than, less than, or not equal to. So depending on where your claim is. So remember, it's just the same as before. One of them has to be the claim. If your claim is equal, then your claim becomes x0. If your claim is greater than, less than, or not equal, then your claim becomes HA. Okay, so that's actually how you figure out your conclusion. If there is significant difference, if there is significant sample that is different from 0, then that means you have a very surprisingly high or low sample. Then you say there is sufficient evidence. And if your x0 is claimed, then you use the wording reject. Otherwise, you use the wording support. When you run StatDis, other than the p-value, they also have a confidence intervals that they produce for you according to the significant difference. And how do they come up with the confidence interval is, if you are doing a two-tailed test, then C level is 1 minus alpha. Otherwise, it's 1 minus 2 alpha. So you can actually also use the confidence interval with any other C level. You don't have to use the one that is produced by StatDis after they run hypothesis test to do a conclusion. There is another, you can actually just run something here. So if you don't want to use, so like see, for example, if you run the mean, two independent mean, right? And you just take this and you do evaluate. You will have a p-value and all those, and see how they would always give you a confidence interval, but it is all fixed based on the significance. So if you want to get another one, you would just do analysis confidence interval. There is a mean to independent samples also. You can use data, you can use statistics, and then you evaluate. So you would be able to get whatever that you want. I want a 98%, so you can run it, and they would produce another confidence interval for you, which you can control the C level basically. Otherwise, you can use the one from the hypothesis test. If you are doing just the confidence interval, you can also make conclusions, just like in proportion. If the interval contains 0, then you can conclude that mu1 and mu2 has no significant difference. They could be the same. And in most cases, how can they contain 0? Is the lower limit is negative, the upper limit is positive. If the interval is all positive, then you conclude mu1 is greater than mu2, because when you subtract two numbers and you get a positive number, it must be mu1 is always higher, or mu d is higher. And if it is mu1 is if it is containing a negative number, that means mu1 is lower. Okay. So here, the notes is, when you do conclusion from hypothesis test and confidence interval, basically the conclusion are the same because they're using the same standard deviation or standard error. And remember, in all cases, at least in this course that I'm doing, we always assume that the variance are not poor because they are not equal and unknown. Okay, so we always almost 100% use t-distribution. Example 1, so I'm going to run an example. this is a really basic one. They want to compare mean enrollment for 2-year college and mean enrollment for 4-year colleges. The claims say that the mean enrollment at 2-year college is lower. Okay, the first is lower. So you see there's two things that they're comparing. The two samples, and then they collect two samples from the first sample, that is the 2 years. So you can see that they talk about 2-year colleges first, right? So there is reason to just define this as population 1, and then you would do this as population 2. And because this is population 1, let's look at the summary. They do 35 colleges, so that would be N1. They also do 35 4-year colleges, that's N2. The mean enrollment for N1 for the first sample is X1 bar, right? And this is the S2, S1. For the 4-year college, this would be X2 bar, and that would be S2. So you collect all those data, write them down because there's so many data around. We also have sea level over here, right? So these are what you need to collect first. Let me write this down because we want to enter it. So population 1 is the 2 years. Population 2 is 4 years. And then both N are 35. But the first one is 5068 with the standard deviation of 4777. The second is 5466 with standard deviation of 8191. Okay, so when you read this, that's what you do. First of all, collect all the information and write it down. So because there's two independent samples, some are 4-year college, some are 2-year college. They're not affiliated with each other or pair up. It just so happened that they have 35 in each. And then so you would want to make sure that which one is 1 and which one is 2, right? So 2-year is population 1, and you write down N1, X1, S1. Population 2, 4 years, N2, X1, X2 bar, S2. Both sigma are not given. And then because we're saying the 2-year college has a lower mean enrollment, so the claim would be mu1 is less than mu2. The null hypothesis is mu1 equal to mu2. So in the null hypothesis always 0. The alternative would have to be the claim because otherwise it doesn't show up, right? Significant level is 0.05. It's a left-tail test because the arrow points to the left, and we use t-distribution. Now we're going to run it. So the command that we use is analysis mean two independent samples because they're independent. So I'm going to clear all this first. And I say analysis, hypothesis testing, mean two independent samples. First is to choose the null hypothesis, that is mu1 is less than mu2. Mu1 less than mu2. So it's a left tail test. Significant level 0.05. Sample size 35. I've written it down. 5068. And then the sample standard deviation is 4777. The other one would be also 35. Mean is 5466. Is it 5466? Standard deviation is very large. 8191. I'm going to double check that it is 5466. Yeah. Did they say 5466? 5466. Yeah. Okay. So we don't know the population standard deviation, but it doesn't matter. The last one is unequal variance. We assume that we don't know, and they're unequal, so evaluate. So that's what you need to enter. 2 sets of sample, but make sure that you don't mix them up because the direction is here. It's important. So the test statistics is negative 0.25, p-value of 402. 402, right? p-value negative 0.25. That means your sample is less than the mean by 0.2 standard deviation, and the chance of getting this sample is 40% if x0 is true. x0 said that there's no difference. So, and then you also have written down this confidence interval 3079, 22x3, right? 22x3. So let's do the conclusions. Because p-value is greater than 0.05, we fail to reach x0. x0 seems to project this sample very well. And so my sample is not significant, it's not surprising. So we use not sufficient evidence. Because the claim is in the alternative, because we say the claim is, we claim that there are lower enrollment in the first one, right? But so it is HA, so we say not sufficient evidence to support it. We cannot, because X0 actually kind of predict what the sample is. The sample, there's 40% chance to get that sample. So cannot support the claim that it is less than those at four-year college. So they could be actually the same. So that's what you do if you do a hypothesis test of two independent samples. The second example is do the same thing, but you have two samples comparing the mean life of two types of battery, the Duracell and the Ever-Ready batteries. And then they do some samples, a small sample, because I think these mean life, battery life are usually normally distributed. So a small sample is fine. So 8, 41 and S1 Ever-Ready, N2, 10 battery only. The mean is 45, the standard deviation is 20. So they are independent because there's no way each battery pair up. And actually, if you see the summary data, they are actually independent because you can't find a pair difference anymore. So we just divide the population. They are already written in really nice form, so I just do not need to copy it down. So if they're written in like a paragraph, then you should line them up, but this is already well written. So we just do set this. What are we doing? We are just to estimate the difference in mean life, estimate how much the difference is, the mean life is. So there's no need for hypothesis, and they are given us a confidence level, which is 95. So you just go to stat this and run. So go to set this and then run confidence interval, but mean two independent sample. Say 95%, input the data. Oh, did I copy it down? N1 is 8, 41, 18. N2 is 10, 45, 20. And we don't need to give them claims. So confidence interval is really convenient. So you just put your sample here, 41, 18. Sample size 2 is Ever-Ready, 10, 45, 45, 20. Okay, and also we do unequal, no pooling of variances. The confidence interval, 95 confidence interval is negative 23.05. Mu1 minus mu2, 15.05, right? So, and you can see the degree of freedom is 15. It is not 8 or 12. So yeah, so this is the interesting thing is degree of freedom, p-value is 0.66, and then the main thing is you estimate how much is the difference. Oh, you see that there is a negative on the lower end and a positive on the upper end. That means 0 is in the interval. Okay, so copy down the number. And because 0 is in the interval, there's significant difference. The difference can be as low as negative 23, as high as 15. But technically, we would say there is no significant difference because they could be 0. So concluded the mean life for the blue battery has no significant difference. They are statistically the same. The sample shows a difference of 41 to 45, but actually those are because of sample error. Okay, so we're going to do two more example in the next video.